In the last module, we ended the module with the idea of Prandtl number, which is very important non-dimensional quantity with respect to heat transfer. So, Prandtl number we said is given by this formula mu Cp by K, and it decides how effective is this momentum transport vis-a-vis heat transport. Both these quantities, both these transport of momentum, transport of heat happen because of certain physical properties of the fluid. Viscosity is responsible for transport of momentum. Alpha or thermal diffusivity, this you would have seen when we derived, when the conduction equation was derived. What is this quantity alpha? Alpha is, so remember this, we have del square T is equal to 1 over alpha dt by dt q dot plus, this was your conduction equation, and this was 1 over alpha is nothing but rho Cp over K. Therefore, alpha is equal to K over rho Cp. This quantity, thermal diffusivity, is responsible for how effective the mass, the momentum, the heat transfer is there. This alpha tells you K refers to the thermal conductivity, rho Cp is a quantity which is used to indicate the energy storage. Larger the thermal diffusivity, in comparison with rho Cp, the K is going to be large, the thermal conductivity aspect would be large. So, Prandtl number is defined actually as nu over alpha. Nu is nothing but your mu over rho, and alpha, 1 over alpha we wrote as rho Cp by K, and that is how you get this form mu Cp by K, which we saw here. So, this definition nu over alpha is very significant. Why so? What is there in the numerator is viscosity. It looks plain viscosity. This is thermal diffusivity. What does it tell me? It tells me the following: how fast Prandtl number is equal to nu over alpha. This is a quantity which is responsible for momentum diffusivity, momentum transfer. What does the word diffusivity mean? Diffusion is basically how things are going to go into the main flow. If something diffuses, the smell of an agarbatti, incense, diffuses into the room, means it percolates into the room, it permeates into the room, it is there in one corner, and over time the entire room has the fragrance. Okay. So, similarly, because of this viscosity, momentum is being transferred, it is being transported from one part of the fluid to the other part of the flow field. This versus thermal diffusivity, which is the alpha term. This quantity is so significant. What does it indicate? It says how effective is momentum diffusivity in comparison, when compared to how effective is heat transfer. See, certain people have affinity for certain things. Okay, so a fluid also is like, it's not going to behave the same way with heat transfer as regards momentum transfer. It may be able to transport heat better and momentum little slower. Okay, I, as a student, we have this question, Prandtl number, oh, it's a non-dimensional number, what is so great about it? No, there is a great deal of significance to Prandtl number, because Prandtl number is what distinguishes the class of fluids. Low Prandtl number, high Prandtl number fluids indicate varying differences, varying spectrum of applications. Liquid metals, for example, very high thermal diffusivity. So, Prandtl number is extremely small. What happens because of this, I will show you later in this lecture. This difference in the Prandtl number causes a lot of significant changes in how I even solve the governing equations. Okay. And this at an undergraduate level we do not teach the students, but if as teachers we are aware of this concept, it will help us communicate these the basic convective heat transfer aspects very well to students, because many of them will have this question, but since it is not a part of the syllabus, they will not bother asking it. As a part of the lecture itself, if you introduce these things, it will be very good. So, momentum diffusivity versus thermal diffusivity, how far the momentum is being transferred versus how far the heat is being transferred. If you keep, say for example, time as the fixed quantity, how far in the given time, how far has the momentum gone from the flat surface, how far has heat gone from the flat surface. Okay. Or if you keep the distance fixed, if this is the plate, flat plate, I am looking at this point, has how long does it take for momentum to get transferred from this to this part, how long does heat take to come from here to here. So, keep either the location of interest fixed or keep the time scale fixed. You would see that most fluids would behave differently with respect to momentum and heat transfer. That quantity is given this non-dimensional number, Prandtl number, nu over alpha. So, obviously, we can say Prandtl number can have 3 different values: less than 1, approximately equal to 1, greater than 1. Very nice. So, less than 1, greater than 1 or equal to 1. How does this physical transport manifest itself in the growth of the boundary layer? This is something which is very, very important. When I have Prandtl number approximately equal to 1, okay, what it means is that the hydrodynamic boundary layer delta of x, this is my y direction, this is my x direction. I am not writing u infinity, t infinity again and again, it is all understood by now. What we say is the momentum transport from here to here is similar to the energy transport. The curve shown in purple is the thermal boundary layer. These two boundary layers are kind of the same dimension, the growth rate is also similar. This is for Prandtl number equal to 1 or approximately equal to 1. What happens to the velocity and temperature profiles? Velocity profile would go from 0 at this wall to u infinity here. Temperature profile will go from T wall here to T infinity in this part. Okay. So, you have both extending almost to the same location in the y direction. This is Prandtl number approximately equal to 1. Now, let us go to the case where Prandtl number is greater than 1. So, delta of x of the order of delta t. Prandtl number greater than 1, that is nu over alpha greater than 1. That means the fluid would transport momentum much far away as opposed to transfer of heat. So, this is my y, this is my x, and what you are going to see is delta of x is going to be greater than delta t of x. Okay. Now, if I were to draw the velocity and temperature profiles, temperature, what is the boundary layer? It is a demarcation of the region where the temperature starts to become equal to free stream temperature. So, here alone We would have variation in temperature only in this part, and all along after that it's a constant value. This is all T infinity. So, for 0 less than or equal to y less than or equal to delta t of x, t of x comma y is between T infinity and T wall. Y greater than delta T of x, T is equal to T infinity. Is that clear? For this portion, this part, T infinity is between, T local is between T infinity and T wall. What about velocities? Hydrodynamic boundary layer indicates that the velocity is going to go all the way up to u infinity, all the way varying up to this location. So, 0 less than or equal to y less than or equal to delta of x, velocity change is happening over a greater distance, temperature change is happening over a smaller distance. Very, very important. Okay. Now, if I do the same concept for Prandtl number smaller than 1, I am taking a fresh sheet, not putting it there. Prandtl number less than 1. X, y. What it means? Delta T local is greater than delta. This is the first thing, and after that we are going to see several things. Boundary layer, hydrodynamic boundary layer ends here, which means my velocity distribution is only between 0 and delta. Afterwards it is the same everywhere, u infinity, T infinity. Temperature distribution is going to be changing like this. So, T wall, T infinity here. In this case, this is u infinity here. So, velocity is varying everywhere. Velocity is varying only in this part. It is all equal to u infinity here. So, if I have to write similarly, 0 less than y less than equal to delta x, u is going to vary between 0 and u infinity. Delta of x less than y less than delta t of x in this portion, region 1, region 2, region 3 if I call. This is region 1, this is region 2, u of x comma y is equal to u infinity. Region 3, y greater than delta t, u is equal to u infinity. So, the fluid mechanics part is basically region 2 and 3 are identical as far as fluid mechanics is concerned. Here, as far as heat transfer was concerned, region 1, 2, 3, this is region 1, region 2 and 3 are here, identical. For heat transfer, Prandtl number greater than 1 case, these two regions are identical because the temperature is equal to the free stream temperature right after this. Velocity is equal to the free stream velocity right after delta. Okay. Now, if I write for the heat transfer part, 0 less than y less than delta of x, region 1, temperature is varying. T infinity less than T of x comma y less than or equal to Tw. Region 2, delta of x less than or equal to y less than or equal to delta T of x. T is still varying. So, we are in this middle where T is x comma y is still greater than T infinity. And finally, in region 3, y greater than delta T of x, T equal to T infinity. So, all three regions are distinct, whereas here in Prandtl number greater than 1 case, for hydrodynamics, 1, 2, 3 are distinct. For heat transfer, 1 is distinct, 2 equal to 3, because T equal to T infinity here. Here hydrodynamics, 1 is distinct, 2 equal to 3, because U equal to U infinity right here. In heat transfer, all regions are distinct. Well, I have written all this. What does this mean? This is very important because it tells me what I need to do in solution of governing equation. We have not derived the energy equation, but we all know what fluid mechanics Navier-Stokes equation is going to be. Navier-Stokes equation is just nothing but law conservation of momentum, Newton's second law, and I will write only the x momentum equation for you, and you will understand how things become simple. Rho du by dt plus u du by dx plus v du by dy plus w du by dz is equal to minus dp by dx plus mu d squared u by dx squared plus d squared u by dy squared plus d squared u by dz squared. This is your governing equation. Okay. And boundary layer is typically steady, 2D, etc. So, this will go, this will go, this will go. Okay. Now, this is your simplified x momentum equation. Let us take the case of Prandtl number greater than 1. See, what is my idea? My idea is to solve for velocities and the pressure. That is what momentum equation is going to give you. 3 momentum equations, x, y, z. Pressure is the unknown, continuity equation is there. So, 4 equations, 4 unknowns, things are solvable. A crude way would be to solve the entire set of Navier-Stokes equation, x momentum, y momentum, z momentum equation over the entire flow field and not bother about anything. Okay, that is not the smart way of doing. The smart way of doing it is would be to segregate it into parts where things are going to be different, and we make use of the fact that you are going to have this kind of a behavior or this kind of a behavior. Okay. So, let us take PR greater than 1 and PR less than 1 case. PR greater than 1, if I am just going to draw this diagram on the side, PR greater than 1, delta greater than delta T. So, this is my delta, this is my delta T. Okay. My velocity distribution is going to go this, temperature distribution is going to do this. Okay. So, I have in region 1, I will write this in for 3 regions. So, region 1, u is completely varying. So, I have the equation remains just as what it is, du by dx plus v du by dy equal to minus dp by dx, this is 1 by rho of course, plus mu d squared u by dx squared plus d squared u by dy squared. This is good. Region 2, in region 2 again there is no change in the velocities, u is varying here, it is not reached a constant value. So, du by dx plus du by dy equal to same quantity. And that is what I told you before also, my equations for hydrodynamics, we have distinct 1 and 2. Velocity is going to be different here in region 1, in region 2 it is going to be different. The equations would be complete as you see here. You would have to solve identical equations with different boundary conditions. In region 1, u equal to 0 at the wall has to be satisfied. In region 2, this would be something like this, and you will not typically solve for 1 and 2 separately, you will take these two together. Okay. So, what happens in region 3? Life becomes easy. U is equal to u infinity, we saw that, u equal to u infinity here, and therefore, du by dx equal to 0. V is 0 in this part because u is a constant. Continuity equation tells me du by dx plus dv by dy equal to 0. If u is constant, du by dx is 0. Therefore, dv by dy is equal to 0 and the velocity is identically equal to 0. You have seen this in fluid mechanics. So, in the free stream, v is also 0. So, the left hand side of the momentum equation is u into 0 plus u is constant everywhere. Therefore, all derivatives are 0. If all derivatives are 0, second derivatives are 0. This gives me dp by dx is equal to 0, and this result becomes very useful later on. Okay. So, I would not go and solve the entire Navier-Stokes equation for the whole flow field. I will just solve it from 0 to delta and make use of my understanding that u equal to u infinity and just get dp by dx equal to 0. Now, let us take for Prandtl number less than 1 case. Here we are going to see difference in the Navier-Stokes equation. So, Prandtl number less than 1, this is your delta T, region 1, region 2, region 3. I have to solve the energy equation because when I am talking of a thermal problem, I am going to solve the momentum and the energy equation. Energy equation means I have to go beyond y equal to delta T. So, Navier-Stokes equation, the identical simplified boundary layer equation is this. I will just write down rho u du by dx plus v du by dy equal to minus dp by dx plus mu d squared u by dx squared plus d squared u by dy squared. Is that right? So, when I see this, what am I going to write? For region 1, u is varying, okay, 0 less than u infinity. So, the equation remains as it is, rho u du by dx plus v du by dy equal to minus dp by dx plus mu d squared u by dx squared plus d squared u by dy squared. No change here. Okay. So, region 1 in both cases, PR greater than 1, PR less than 1, same equation as PR greater than 1 case, because that is the boundary layer, na? So, it is going to be identical, there is no change. Region 2, u equal to u infinity, therefore, all the gradients will be 0, v is 0, we saw that, we saw v equal to 0 here, same thing, v is 0 here. So, my governing equation would be rho u infinity 0 blah blah blah, you will get exactly minus dp by dx plus mu into 0. So, what do I get? dP by dx equal to 0. And obviously, region 3 also same as 2. Where does this lead me to? Well, when I have energy equation, we have not derived the energy equation. I will just write the term of on the left hand side for the energy equation. Energy equation is going to look like simplified form u dt by dx plus v dt by dy equal to several things. Prandtl number less than 1 case, I have region 1 energy equation would be left hand side of energy equation stays as it is. That means this part will remain as it is. Now, when I have Prandtl number less than 1, region 2, this part, region 2, where I have velocity equal to u infinity, but temperature varying, I have to solve this equation. What will I write? Rho Cp, instead of u, it will be a constant dt by dx. Now, look at this. V is 0 in region 2, so this term will vanish, and right hand side also will have several simplification. I am just trying to highlight a very important thing here. I have got one simplification already on the left hand side. I have not gone to the right hand side. Okay. So, the point being, instead of blindly solving governing equations just the way they are, if we use this concept of Prandtl number, if we use this concept of thermal boundary layer thicknesses being different, we will greatly simplify the governing equations. We will be able to solve them easily, we will be able to save computational costs and computational time, and therefore be a better, we will be able to do the computations in a smart manner. Just to recap, Prandtl number, ratio of momentum diffusivity to thermal diffusivity, how far or how fast the momentum is being transferred to how fast or how far the heat is being transferred. Thermal boundary layer and hydrodynamic boundary layer are each different. They are responsible for, they are representative of how far the transport has happened. So, PR to the power n is this. This is what is typically given in textbooks. Momentum diffusivity manifests itself as boundary layer thickness, hydrodynamic boundary layer thickness, how far the momentum has gone, delta of x. How far the heat has gone is delta T of x. So, this ratio is not equal to Prandtl number. This is a mistake which students make. It is actually of the order of, this sign means. Prandtl to the power n, n is less than 1, okay, 0 less than n less than equal to 1. So, Prandtl number to the power n gives you an idea of how fast the thermal boundary layer is growing versus how fast the hydrodynamic boundary layer is growing. Momentum transport is manifested by hydrodynamic boundary layer growth, thermal transport is manifested by the thermal boundary layer growth. These two transports may not be the same. A fluid may be partial to transport of momentum versus heat, or may be partial to transport of heat. This is taken care by this Prandtl number. Thank you. In the next module, we will go to what is called as fluid particle acceleration and finish what is Reynolds transport theorem, which will be a precursor to derivation of the continuity, Navier-Stokes and the energy equation. Thanks.